Hello, everyone. My name is Sharon Xie. I'm a founding engineer at Decodable. Today, I want to talk about the top three challenges running multi-tenant Flink at scale. I actually gave this talk at Flink Forward this year, but unfortunately, it was not recorded. Ever since, I've got asked a lot about this talk, so I'm recording this again. So a little bit about myself. I've spent the past 5 years using and managing Flink and I've experienced a lot of challenges. So today I want to share about those challenges and the trade-offs we've made, particularly at Decodable. So Decodable uses Flink a lot. It runs all the data processing jobs. Decodable offers real-time data processing as a service, and internally we use Flink a lot. It runs all the data processing jobs, and we use all sorts of deployment modes for different use cases, and I'll talk a little bit more about this later. As for challenge, I want to share a story at a previous life at a different company where I was also providing service, a data platform service for internal users. I realized people ask me a lot about what's the difference between save points and checkpoints, why sometimes my job failed and I cannot restore from it. Um, what are those, what's the configuration I need for my job to work as expected? All sorts of issues made me realize that there are a lot of Flink low-level details that's that's using users' time. So instead, they could use that time focusing on, writing their business logic. So the first challenge being, how do we abstract Flink away? We know Flink is powerful and flexible, but it's really complicated, like I already mentioned. So instead, we think it's possible for users to just think about how do I connect to the data sources and things, and how do I write my declare my data processing logic. We know that SQL is a popular language that a lot of people already know. It's declarative, and that's what we use at Decodable. But SQL itself doesn't just solve all those problems. We really want to abstract away those low-level details, like I said, about distributed checkpointing, state management, all sorts of configurations. Instead of thinking about Flink deployments, we want users to really focus on the data processing logic. So here is the diagram of our conceptual model. It actually just maps to what users would do to perform data processing tasks. User would configure source connections, which is a job for the connector, gets the data into decodable streams, and then writes pipelines to process the streams. The output of the pipelines goes to another stream, which again can be consumed by sync connections to get to the data out to their external systems. But today I don't want to focus on a lot about our user experience design. I want to show you what's happening behind the scenes. So this one shows we use Flink to run connections and pipelines. For streams, we use Kafka as the storage. So an end-to-end workflow has 3 Flink jobs. You can argue that, hey, I can do this whole thing with just one Flink job. I don't even need a Kafka system in between. Why is the system designed this way? In fact, that is an explicit trade-off we've made. This abstraction has not only made the user experience clean and intuitive, as I mentioned, it maps to what a user would do. This separation of connectivity and processing also made our architecture clean. It also enabled us to build a lot of interesting features on top of it. So as an example, let's take a look at the different responsibilities of connections and pipelines. Again, they are Flink jobs, but I'll show you why they are different. Sections handle connectivity with external systems. So you can imagine there would be very specific connector configurations. It lists records with a valid schema to pass through our system. So those Flink jobs are usually small pass-through jobs. So the Flink state is usually very small. On the other hand, pipelines handles data processing logic. The Flink state is really very based on the query. Also, because we have those internal streams that are backed by Kafka, the sources of things are always the same for pipelines. This actually made our pipeline jobs very stable because we know that there's only one type of source and one type of sink for their job. So as you can imagine, when connectivity issues happen for pipelines, we know exactly where the issue is. Another good thing about the internal streams is that the records in the streams are already in valid forms. Again, remember connections would only let records with valid schema to pass through. So in this case, our pipeline job would not encounter the runtime errors such as a bad records would jam the processing and the job just fail. So in short, this model, this abstraction actually made our architecture very clean and stable. Also, it promotes the clear ownership, responsibility, and access control. As you can imagine, if you have a team of engineers, some of them are managing the infrastructure, some of them are data engineers. You can have the infrastructure engineer to configure the connections and having the data engineers to focus on the pipelines, and you can apply different access control rules for different teams. This architecture also promotes reusability, so each stream can be consumed by multiple consumers, either being another pipeline to reprocess the records, or you can have multiple connections consuming the same stream. Also, the well-defined contract made it very interesting and easy for us to provide workflow automation. So, for example, if you want to make a schema change, and we internally track the relationships of all the resources you defined, so we know the full dependency graph, and we can help users to apply the same changes based on the dependency graph and automate it. Last but not least, like I mentioned in the previous slide, the pipeline jobs and connection jobs have different trees, and that allow us to do different Flink configurations for different optimizations, particularly to their trees. And also we can scale separately for those jobs. So if you have a processing heavy job, we can increase the resource for the pipeline without impacting the connection. So in short, we built another abstraction layer on top of Flink, and we've made some really hard trade-off between more resource consumption versus better user experience. The next challenge I want to talk about is managing isolation. And this is super typical for data platforms running in the cloud, given that we are touching and literally processing the data coming from different users, different organizations. This is a very important topic. On the other side, there's always the balance between reducing the cost with more resource sharing versus increasing the risk of more noisy neighbors, more blast radius, bigger blast radius, and potentially lower security. So how do we think about that? At the Decodable, we slice the isolation in 3 different layers. At the infrastructure layer, we isolate hardware resource. At the data processing layer, which in our case are Flink jobs, we make sure that the jobs are isolated. At the configuration storage layer, we also want to treat secret configurations separately from normal configurations. The secret configurations are, the credentials for accessing the external systems. I'll go through each of the layers in the following slides. For infrastructure isolation, as I mentioned earlier, there's a balance between cost effectiveness and more security. So the short answer is that there is no one size fits for all. So instead, we make it flexible to configure. In our our deployment unit is a cell. A cell essentially runs a control plane and a data plane, and we can put multiple accounts inside the same cell. In this cost-effective deployment, a cell is on a Kubernetes cluster, but there could be multiple cells on the same Kubernetes cluster. They are in different namespaces, of course. Similarly, for DB cluster, it's a shared cluster that's namespaced by database that's serving different cells. Similarly, for Kafka cluster, this setup is very suitable for our free tier and on-demand tier, where we want to pack many accounts together so that they have a shared infrastructure, but at the same time makes the cost really low, really affordable for users. A good side effect of this deployment is because all those hardware resource is already created, the deployment speed of adding a new account for us is very fast because there's no additional hardware to provision. On the other side, there are always more sensitive customers, either for security reasons or performance reasons. They would prefer a much more isolated environment. So we actually can configure our infrastructures differently by, as an example, by just putting one account inside the cell and give that cell dedicated Kubernetes cluster, DB cluster, and Kafka cluster. So in this way, this single cell gets a dedicated VPC. Internally, we use Terraform to manage our infrastructure. So to create a new cell with different configuration is actually very easy. It's just some lines of code with configuration. It makes it very easy for us to even spin up a cell for a special customer POC or spin up a dev cell for testing. We actually use it a lot. The next thing is job isolation. And this is how we isolate Flink jobs. So we actually use different Flink deployments for different use cases. On the left side, we use preview, mini clusters for preview. And preview is a feature where a user can see a sample output of SQL statements with their data in the stream. So it mimics this traditional database management system experience. And the user can quickly write SQL, see the results, and make changes and see the results. It turns out to be super useful. So those preview jobs are very short-lived, and the result of the job gets streamed back to the user. So the data volume is usually not a concern. If you can see 50 to 100 records, you have pretty good confidence of your query. So because of all those preview jobs are running using mini clusters, For faster response, we use Kubernetes job controller to maintain a pool of mini clusters that are ready to take requests. And for each mini cluster pod, it would just take one request, run it, return the result back to user, and exit. The reason we are doing it to make it just one-time use is because we want to prevent potential data sharing between different jobs. On the right side, we use application mode cluster for our connections and pipelines jobs. The each application mode cluster has a dedicated job manager that's responsible for a particular Flink job. So there's no sharing of job manager for different Flink jobs as compared to the so-called session mode cluster deployment. This makes sure that each Flink job we run is isolated from other jobs. And if one job has a problem, other jobs will continue to run without issues. This mode also is it's much more performant as compared to the previous job setup. So in short, just a quick summary of the two different modes we use. The mini cluster job setup for preview is for fast and quick response where the data volume is low. The application mode cluster is for long-running production jobs. It has longer startup time, but once it's started, it runs very fast. The next thing I want to talk about is how we isolate user configuration and particularly isolate sensitive information. Since we deal with user credentials to connect to external systems, we want to be extra careful to handle their credentials. However, I realized that I can't possibly explain the full story given the time limit. I just want to show a simple diagram here and how we approach it and focus on the principles. So in our case, when a user creates a connection, our API service would handle the request. For normal configurations, like your schema, this kind of thing would be stored in our RDS Postgres instance. For secrets, such as a password, would be stored separately in AWS Secrets Manager. The API service is able to do that because we've configured a service account for the API service that's offered through AWS IAM service. Once the secret is stored in Secrets Manager, no readable APIs, no APIs with read operation can access Secrets Manager. So what that exactly means is none of our API response would be able to retrieve secrets from Secrets Manager. Of course, at some point, that secret needs to be retrieved. So that's when the activation happens. So when an activation request come in, the API service would handle that request and launch a Flink cluster for the connection job. At the same time, it will also go and fetch the secrets from the secret manager based on the requested connection ID and create a Kubernetes secret, particularly masked for the Flink cluster it creates. What that means is the Flink cluster running the data plane that's responsible for one job has only access to the secrets given to it. The Flink cluster has no direct access to the secrets manager, or the secret, nor the secret is shared by other Flink clusters. Hope I made it clear. So like I said, we don't have a lot of time for this. I want to focus on the best practices and the principles here. So one, when you deal with sensitive information, you want to follow the principle of least privilege. Two, you want to minimize the number of services and the number of accounts that have access to the sensitive information. The last thing I didn't mention earlier is audit everything. So we actually audit heavily on the access to the secrets manager with monitoring and alerts in place to make sure that it's it's properly monitored. In if real disaster happens, at least we will get notified and we can just revoke the access to the service account. Okay, so we talk about isolation, quick summary, isolate infrastructure, isolate Flink jobs, isolate sensitive information. The next challenge I want to talk about is about observability. The reason why we need observability internally is because we are offering the data real-time data platform as a service, so things should just work. We of course also commit to SLAs to our customers, and we want to know our performance based on the metrics we identify. To the users, they care about it because they want to know if their jobs are healthy. They also want to understand their performance metrics in case they want to decide whether they want to purchase more or less. The most importantly, they want to get notified if something goes wrong, ideally with actionable messages so they know what to do. However, Flink does not make it very easy for us to do. Let's think about it. Have you thought about how to accurately prove that a Flink job is running? So you may think about, oh, we can see if there are any errors, but Flink is very verbose, and there are a lot of temporary errors where Flink would just do an exception, restart, and recover itself. You you don't want to get a lot of false positives in those cases. And you may think about maybe I can just monitor if there's data flowing in the system, but that doesn't work really well for our case because if you don't see any data being processed, that could just be the external source system doesn't have any data produced. So it turns out that this is not super easy. And this make it harder because Flink actually offer a tons of metrics at different levels. So finding the minimal set of signals that's generic for all kinds of jobs, it's not easy. But we actually did find something that's super useful, so I share that. For our internal key metrics, we separate those metrics into primary signals and secondary signals. Primary signals are absolute proof of health and functioning. So if they are true, we know our service is working. So the metric we use is the number of successful checkpoints per job, and we monitor that the number is increasing over time. The reason that this is pretty accurate is because Flink periodically emits checkpoint barriers, and we've configured for the checkpointing to be in synchronous mode. So it actually operates as a good heartbeat for the system. So when a checkpoint is able to create, that means a Flink job can run from the source operator to the sync operators without issue. Other than that, we also have secondary signals that are useful for debugging or identifying health service degradation. So things like error rates and the number of job restarts, also the consumer lag that will give us good indicator of if there's any back pressure in our system. As for user facing, we selected a half-wall matrix that we think is a good indicator of the performance without showing too much of the internal details. So we have the job level metrics such as bytes in out and records in and out with total. The biggest challenge for user-facing observability for us is actually providing the good error messages. Flink, as I said, is very verbose. So dumping all the error stacks to the users is definitely not a good idea. And of course, there are some times when those errors are not a user fault. So internally, we created an error classifier that would categorize all those exceptions into the 3 buckets. The first one being unexpected server error. That means that's an error we've never seen before. We don't know what's happening. Page our on-call engineer to go and figure it out. The second one being temporary server error is the cause of known errors to us, and we know it will auto resolve itself. A good example of this one is our job restarts with error when Amazon is doing a rolling restart of our Kafka clusters. For those kind of errors, we just monitor it and only deal with it if we cannot repair itself. The last buckets are the ones that require user attention. That means there's nothing we can do internally to fix it. So, for example, when a user configure a Kafka connection and the connection is consuming data from the topic, and they happen to just like delete that topic, our Flink job will fail, and there's really nothing we can do. So for those kind of errors, we would identify them and rewrite them with more user-friendly error messages and send that back to the user. We also provide we also provide users with our internal audit logs and metrics, particular for their account, so user can configure their own monitoring systems. For example, Elasticsearch or I don't know, Splunk, Datadog, to consume the logs and metrics that we provide. All right, so that's all about the 3 challenges I wanted to share. A quick summary. We talk about abstract Flink away. We talk about how to isolate at different levels for a service. We also talk about how to create good monitoring and observability for for Flink. So if you look at those challenges, I think these are actually very good ones. The fact that we don't struggle with scaling Flink up or fixing random Flink bugs mean that Flink runs very reliably for us. So the cost of those challenges to me are really just a lot of expertise is needed to make good decisions. Think about those massive Flink configurations with different APIs and different deployment modes. It takes a real expertise to know what's the right thing to do. And with the cloud infrastructure, you need to know the networking, operating systems, distributed systems, security rules. That's just a lot to deal with. So for us, we think that the scalability for Flink actually means how do you increase the number of users who can do real-time processing? And to us, the answer is clear. The key is to offer data processing, real-time data processing as a service with one, multi-tenancy support that would reduce the cost, and two, with added layer of abstraction to make it easier to use. And that's all for my presentation. Thank you.